You may have encountered the term entropy before. In chemical and physical systems, it's a state of chaos of the system. In statistics, it's a property of a random variable. The entropy of a discrete random variable is a number that quantifies the uncertainty inherent in its possible outcomes. And there are mathematical definitions of entropy, which we'll see in the next few slides. They may seem a bit arbitrary, but they're actually axiomatically defined. Again, references in case you want to visit them. So let's consider, for the sake of example, the case of flipping a biased coin. So let's say I have two coins. Coins, of course, only have two heads, so they can either be heads or tails. And coin 1 gives me this sequence here, and coin 2 gives me this sequence here. Which one of these coins do you think is more biased or loaded?
First one.
The first one seems more biased and loaded, right? Because if we plot out the histogram of the throws, we'll see that it's heavily weighted towards one side. So how do we put a number to this? This is where entropy comes in. So the entropy of a loaded coin with probability P of coming up as heads is given as h of x is the negative sum over the probability of x times log in base 2 of that probability. In the case of our space of possibilities being a binary space, then it becomes this expression here. So if we write it out, we have, based on our observations, we know that P is equal to 8 over 9 for the coin on the left-hand side. We will write minus 8 over 9, log 2 of that, and then minus the other case. It comes out to be something like 0.5. Whereas for the more fair coin, where probability of, let's say, heads is 4 over 9, that comes out to be closer to 1. So the coin whose outcomes are more certain have lower entropy, right? This is the coin that is more certain, and that means that we have lower entropy in the system. In the extreme case, where probability of heads is either 0 or 100%, then we would be absolutely certain of the outcome of the coin even before throwing it, right? So we don't really have any information to gain from having a random draw. What would the entropy be there? Guru?
0.
0.
Right, so in that case, we'd have minus 0 times log 2 of 0 minus 1 times log 2 of 1, and that comes out to be 0. So in the cases where there is no uncertainty, where we said P is equal to 0 or 1, then entropy is also 0. So we gain no information by observing a new flip. Now, you can also think about entropy as the expected, as I've been pointing out, as the expected information content of a random draw from a probability distribution. So this is the probability between 0 and 1 of a coin coming up as heads, and on the y-axis we have the entropy. If at the middle here P is equal to 0.5, if we have a coin that's completely fair, then that has the most uncertainty in the system, and that can be characterized by having the highest entropy among all other cases. So the most difficult to predict coin is a fair coin, and seeing the result of a fair coin gives you one full bit of information. And so the units of entropy are bits, and Cloud Shannon also showed that you cannot store the outcome of random draw using fewer expected bits than the entropy without actually losing information. Okay, let's continue with the example of a loaded coin then. The entropy of a loaded coin with probability P was given as such. And we said that if we have high entropy, that means that the system has a distribution which is a bit uniform over the outcomes that can occur. Whereas if a system has low entropy, that means it's very concentrated on a particular set of outcomes. I promise we'll get back to decision trees, but you'll have to bear with me for entropy for a few more slides. Okay, so suppose now that we observe partial information X about a random variable Y. In this case, Y is whether or not it's lemon or an orange, and the information that we observe is, for instance, whether or not the width is larger than some threshold. What we want to address is what is the expected amount of information that will be conveyed about our output Y if I observe the information X, if I make a particular split, then how much information gain will I get about my target? That's the goal. And so to answer this, we need to study a few things: joint entropy, conditional entropy, expected entropy, and finally information gain. And then we wrap it up and bring it back to decision trees. Okay, so consider the system here where we have two variables. We have whether or not it's raining and whether or not it's cloudy. Let's say this corresponds to London. And this is information measured over 100 days, where we collected two features over those 100 days. The joint entropy would measure how much uncertainty there is in both of these two random variables together, where one of the random variables is a binary, is it raining or not, and the other one is binary, whether it's cloudy or not. Now, already from this table, we can see that if it's raining, right, so if I look at this row here, then almost for certain it's cloudy, right? Because it has 25 total cases and 24 of them are cloudy. That also agrees with our intuition. If it's raining, there's probably a cloud from where the rain is pouring down. And on the other hand, it says that if it's not raining, then it's slightly more likely to be not cloudy in this case. So maybe not London, maybe another city. But if it's not raining, then it's the majority of the days of the year. But within the not rainy days, it's more likely to not be cloudy, but we're also not sure. How do we then measure the entropy of this system? Similar equation to before, we now define entropy over two variables as this sum over here. We work through the numbers. Again, we have P and then log 2 of P, and then we repeat that over all the 4 cases that we have. And we get some number of bits corresponding to the uncertainty in the system. To test your intuition, which one of these two systems, two different cities, do you think has lower or higher entropy? And why? Guru.
The second system has almost equal probability outcomes, right? Therefore, the entropy is higher.
Right, and what is, Guru, the maximum entropy of a system with n variables?
I'm not sure.
So for one variable, we said if we have a coin with p equals 0 or p equals 1, where we're absolutely certain of the outcome even before throwing it, that's one bit of information.
Right.
In this previous system, which was a bit biased, right? We have 24 and 1. That's rather loaded over here, at least for the rainy days. Our entropy came out to be 1.56. Turns out that in this system, if you write it out, that's 1 over 4, minus 1 over 4, log 2 of minus 1 over 4, and then you continue for all the cases, you get a total bits of 2. So for the case of maximum uncertainty over n variables, the entropy of the system is equal to n. And we can't go below 0 as well. That's the case where we're absolutely certain about the outcome. And I would agree with Guru's intuition here, whereby the uncertainty in the second system is much higher than it is in the first system. The first system, it's rather obvious that it's always raining and always cloudy in the city. Maybe that's Seattle or someplace else. Yes? Okay, excellent. So now with that we understand joint entropy, what does it mean for conditional entropy? Conditional entropy is a measure of how much uncertainty remains about a random variable when we know the value of another random variable. So let's say here that we know that it's raining. We know that X is raining. So how much entropy do we have about cloudiness? Do we think it's a high value or do we think it's a low value within the rainy system? Guru again?
It's a low value.
Low value. Why is it a low value?
It's almost certainly raining.
Right. So when it is raining,
then it's almost certainly
certain that it's cloudy.
Right.
And because we're almost certain that it's cloudy, then we have low entropy in that system. Low uncertainty, low entropy. Yes, no, question marks? Okay, cool. So how do we write that out? Very similar equation again. Just now, instead of it being a joint entropy calculation, it's a conditional entropy calculation. You go through and you get a relatively small value. What is the maximum value again of this conditional entropy in terms of bits? we're only looking at the entropy of one variable conditioned on whatever else. So the maximum value is 1 bit of information, but here it's 0.24. It's a relatively small value. And this was for the case of conditional entropy given that it is raining, and we got 0.24. You could repeat the same thing for the case where it's not raining, and lo and behold, you get a value of 0.92. And of course, this is the value of 0.92 is larger than 0.24. What does this mean then? This means that when it is raining, it's just, quantifying our intuition here, right? What it means is that when it is raining, we have an entropy that's smaller than when it isn't. That means that in the case of it being rainy, we're just more certain about what the status of cloudiness is rather than when it's not. So putting this all together, right, what does this mean? This means that if it's raining, the status of cloudiness is more certain. So to summarize kind of all of these in maybe one box, low bits means we have low uncertainty, means that if we observe something about that system, we shouldn't really be surprised either, right? For a completely loaded coin, you know already what the output would be, so you can't really expect to gain any information from actually performing that draw. Now, again, we're going to come back to decision trees, but remember, why are we talking about this? Because we want to have a criterion for selecting the best splits. And the best splits are those that give us the most information, right? Or that surprise us the most earlier on within our greedy approach. So that's why we're talking about all of this. Okay. And so we can also define the expected entropy of a random variable, and that's straightforward. It's just taking the likelihood of a particular variable that we're conditioning on times its conditional entropy, and we iterate over all possible outputs. Okay. Some properties for entropy. Entropy is always non-negative. At the same time, we said entropy over n variables is capped at n bits. At the same time, it's also lower bounded by 0. There is a chain rule for entropy, like we have for probability. If x and y are independent of one another, then knowledge of x will be ineffective of reducing our uncertainty about y, and therefore the conditional entropy and the entropy would be similar to one another. Becoming aware of one variable cannot increase our uncertainty in another variable. So knowing x, we can only decrease our uncertainty about y. It's just how it is. And if by knowing y, we, of course, are perfectly certain of y, and therefore conditional entropy of y on y is 0. So let's try to bring this back to our problem then with the final preliminary of information gain. What we want to do is we want to see how much more certain will I be of cloudiness if I were to know whether or not it's raining. And so our uncertainty in cloudiness needs to be subtracted by our uncertainty in cloudiness had I observed the value of rain. Right? That's the whole point. So the question is, I'm uncertain about a target. If I observe a particular variable, how much will that reduce my uncertainty in my target variable? And this is the concept of information gain. So information gain about the uncertainty in y conditioned on me observing the variable x is the difference between the initial uncertainty I have about y subtracted by the uncertainty that remains after observing the variable x. Any questions? This might be going a bit too fast. I've probably lost most of you in this entropy information game discussion.
No, Professor, it's quite going very well, actually.
Okay, so good. Sahu understands. Everyone else okay? Questions are absolutely fine, right? We'll see an example of this with numbers. So if it's not clear, I hope it will be in the next slide.